Hi there. Thanks for tuning in to hear my Cosmology from Home talk about a semi-classical path to the cosmic web. I'm Cora Uhlemann and I'm a lecturer at Newcastle University. I will be talking about work done in collaboration with Oliver Hahn, who will also give a talk, Cornelius Rampf, and Matija Gozenka. Now, if you're wondering where Newcastle is, here's a map of the UK cosmology landscape. And Newcastle is the red spot in the north of England, very close to Durham. Now here we have a research group for cosmology and quantum gravity, and actually some colleagues are attending cosmology from home, so hopefully this will give you a taste of the kind of work we do here. Now, I work on cosmic structure formation, and the big question there is, how did our universe evolve from a nearly uniform initial state into today's cosmos with structure on all scales, from stars over galaxies to clusters? And what does that structure tell us about our universe? If we map all galaxies observed by telescopes on the sky, we can identify a network-like structure on the largest scales. And this network-like structure is what we call the cosmic web. And we know that the cosmic web developed from an almost uniform distribution of matter, with tiny seeds of structure that we can observe in the cosmic microwave background. So in the cosmic microwave background, at first order, the distribution of matter across the whole sky is very close to uniform. Only if you look very closely, you can see tiny variations around the mean density of order 10 parts per million. And we know that it's precisely those seeds that caused all the structure we see today. Another thing, we know that most of the matter in the universe actually must be of some kind of dark origin, not all the luminous matter we can actually see. And we suspect that the skeleton of the cosmic web is actually shaped by dark matter as the dominant matter component. And this is a good thing if you're working on theoretical modeling, because dark matter is supposedly a lot simpler than the normal matter we can actually see in the form of galaxies, because dark matter mostly interacts gravitationally. So we assume that the skeleton of the cosmic web is shaped by dark matter as the dominant matter component. And here you can see the output of a numerical simulation that is basically fixed to produce a pattern like we see today in the galaxies. And you can see that the large-scale feature of this cosmic web really corresponds to what we see in the galaxies as well. So now we are facing fundamental questions in cosmology about the nature of dark matter, the properties of the early universe, and also the nature of gravity on large scales. And galaxy surveys that map the large-scale structure can be used as a cosmic laboratory for fundamental physics. And this is the very motivation behind large-scale galaxy surveys that are upcoming, for example, Euclid, LSST, and also DESI. But in order to convert all those exquisite observations into insight of fundamental physics, we need analytical and numerical tools for predicting the nonlinear gravitational clustering of matter. And broadly speaking, there are two approaches to theoretically model the cosmic web. On the one hand, we have numerical simulations of the large-scale structure, and they typically rely on sampling the dark matter distribution with a large number of particles. And this number is called n, and then very often we call them n-body simulations. And simulations generally do well on small and intermediate scales, but it can be tricky to correctly capture the linear growth of structure on large scales. Eventually, simulations are limited by the computational power and require a trade-off between having a large volume and a fine resolution. On the other hand, we have analytical methods that generally rely on modeling the dark matter as a fluid, using its density and velocity field. And this is done using perturbation theory, which is only valid on large enough scales and has a fundamentally limited accuracy in the nonlinear regime. Also, the underlying fluid model limits the features that one can produce analytically. In this talk, I will present an alternative method that can actually be used in both contexts. Our method is based on using one wave function to model the dark matter. And in the following, I will describe how one can use this to develop a new perturbation theory and use it, for example, for high redshift observations or to set initial conditions for numerical simulations. So let's start with something we are familiar with. A particularly simple and popular analytical approximation for cosmic structure is to start from a homogeneous distribution of particles, where initial velocities are prescribed to follow the gradient of the initial gravitational potential. So if we assume that the velocities of the particles stay constant, we essentially just look at the initial gravitational potential, compute the gradient, and then shoot the particles according to this. And this is what we call the Zeldovich approximation, that essentially describes everything in terms of the initial position of the particle, that I labeled as Q here, and then the time at which we are looking, which is here encoded in terms of the scale factor A. So this Zeldovich approximation assumes that the velocity, if you follow a particle at a given time, just stays constant and is given in terms of the gradient of the initial gravitational potential. Now, naturally, if I wait for a time A, the particles will have displaced from their original position to the final position x. Here we can see that the final position x is given in terms of the initial position, and then the displacement that is given in terms of the constant velocity times the time. Now, what can we do with this simple Zeldovich approximation? Let us slightly reformulate what we just said. For the free particle, we can actually easily write down the classical action. Let me remind you, the action is just the integral of the Lagrangian over time. So for a free particle, the Lagrangian just has the kinetic term, so it's 1/2 times the velocity squared. And if we integrate this, we get a result that the classical action is proportional to the displacement of the particle, basically the difference between the final position x and the initial position q, times the velocity, and in our case that's constant, so it's just the ratio of the displacement and time. And let me remind you that our time variable is the scale factor time, so essentially this also encodes the background expansion. Now, what can we actually do with this classical action? We can use it in a slightly different context. Inspired by the quantum classical correspondence, we can use the classical action to transport a wave function. And this wave function will simultaneously encode the density and velocities of all the particles. Now, if we have an initial wave function specified at the initial positions q, we can use this classical action of the free particle here to compute the transition amplitude and convert the initial wave function to the final wave function at final positions x and time a. So now, unsurprisingly, the wave function that follows from the free propagation follows a free Schroedinger equation. And essentially, this is the semiclassical analog of the Zeldovich approximation. But we introduce the free parameter here. hbar essentially is a new parameter that sets the resolution scale. And it appears both in the Schroedinger equation here and also in the formulation of the transition amplitude. We will treat hbar as a free but small parameter and work in the semiclassical limit where hbar is kept non-zero but always very small. So how can we get some kind of insight in what this means? What does this wave function represent? Here I show an example of the free propagation in one dimension. So in one dimension, all we have is basically a scalar position x and the time a. And we start from simple initial conditions that correspond to a sine wave. So we have a wave function that essentially has a uniform amplitude, which is just 1, and the phase is specified such that particles essentially move to the center. So that really corresponds to the Zeldovich approximation. And here in this plot, the amplitude is shown by the brightness. So very bright spots are high amplitude, so high density. And the color indicates the phase of the wave function. So if we follow a line of constant phase, this basically corresponds to particle trajectories. So we start from a uniform density, kind of uniform brightness here, and particles move to the center. And as we expect classically, there would be some point of shell crossing where the first particles cross in the center. And this gets converted to this bright spot here, where the density is high, but it's always finite because we introduce this parameter hbar that regularizes everything. After shell crossing, you can see that the wave function shows interference, and we have this kind of classical shell-crossed region. It's bounded by some kind of density, which is very large, but it's regularized, so it's not really infinite as it would be in the classical case. Now, from random initial conditions that roughly correspond to the cosmological case, one can produce a similar plot. And we can see here, just looking at the brightness, that this actually features a cosmic web-like pattern here. And this is the eventual idea to basically use this to set initial conditions for numerical simulations. Now, while the Zeldovich approximation corresponds to a free Schroedinger equation, in general, one has a Schroedinger equation with an effective potential. And in the perturbative regime, this effective potential can actually be computed from standard perturbation theory, so just solving the fluid equations. And propagator perturbation theory is based on solving the Schroedinger equation given an external perturbative potential. And as I said, this potential can be computed from perturbation theory, and we can see here that while it vanishes at first order, the second order encodes some kind of tidal effects. So you see differences between second derivatives of the gravitational potential here. And interestingly, this effective potential is actually time independent at second order in perturbation theory. Now, in propagator perturbation theory, one solves the Schroedinger equation with the given effective potential. And we solve this by determining the propagator, which essentially specifies how particles propagate from initial position to a final position. So it starts from position x, q, goes to position x in time a. And now it's convenient to split this propagator into the free propagator from before and an additional tidal contribution that is induced by this effective potential. And then we can write this solution in terms of the effective potential evaluated at the initial and the final position. And this has a straightforward meaning. If we think about a numerical scheme, essentially I perform a kick to the particles according to the effective potential at the initial position. Then I drift my particles, so I basically just do a free propagation to the final position. And then I kick them again according to the value of the effective potential at the final position. So with this propagator, I now know how to convert an initial wave function to the final wave function by basically just propagating it. Now, once I have my final wave function, I can determine a phase space distribution and classical observables like density and velocity. So the phase space distribution is computed from the wave function using the so-called Wigner distribution. And a crucial point is here not really the expression, but the crucial point is all phase space information is in the wave function. And in particular, based on this phase space distribution, I can read off both Lagrangian quantities like the displacement and Lagrangian velocities, but similarly one can determine Eulerian quantities like the density and velocity. So if we extract the Lagrangian displacement and velocity, we find that our second order propagator perturbation theory corresponds to this displacement field from second order Lagrangian perturbation theory. Now, the velocity we get is also consistent with second order LPT, but it includes an additional term that actually ensures the conservation of vorticity. So what does this vorticity conservation mean? It's very simple. Before shell crossing, there's no Eulerian vorticity, so the rotation of the velocity is zero. And this constraint can actually be translated to Lagrangian space. And there it's called a Cauchy invariant. And the crucial point is that if you do perturbation theory, this invariant can be violated according to the perturbative order you're looking at. And if you compare the propagator perturbation theory we're doing here, this violation is actually less strong than it is in standard Lagrangian perturbation theory, essentially because the symmetry is protected in the Schroedinger formalism we are using. Now, the density and velocity is easily obtained from the wave function and its derivatives. So this now means that propagator perturbation theory can be used as an analog of Lagrangian perturbation theory that straightforwardly produces Eulerian fields. And this proves very useful for field level predictions at high redshift. For example, for the Lyman alpha forest, as has recently been shown by Porqueras et al. In the recent archive paper. And similarly, propagator perturbation theory can be used to set initial conditions for numerical simulation. And this is particularly relevant for hydrodynamical simulations that need Eulerian fields as an input. So for this purpose, we have generalized the formalism to two fluids, describing both dark matter and baryons. And we included the dominant effect of a relative initial density between the two fluid species. But we neglect decaying modes such as relative velocities. In this setting, one can simply apply the single fluid propagator that I described here to the wave function for each fluid species. So all one has to do is to set up the different initial conditions for the wave function and then propagate them with the same propagator. So please have a look at Oliver Hahn's talk about the next generation of initial conditions for cosmological simulations. And let me wrap up and conclude and provide a quick summary of my talk. I hope I convinced you that the large-scale structure is not only very interesting, but can also be a powerful cosmic laboratory to probe fundamental physics. But the challenge we are facing here is to describe the nonlinear gravitational clustering of matter. And for this, we need both analytical methods and also numerical simulations. In this talk, I described using a semiclassical tool to approach this nonlinear clustering of matter. And the idea is based on the correspondence between classical and quantum dynamics. Everything in our formalism is centered around the Schrödinger equation with an effective potential that you can determine, for example, by standard perturbation theory. And then you can compute propagators, and we found that with the propagator, we basically have an analog of Lagrangian perturbation theory, but we can straightforwardly obtain Eulerian fields. So in some sense, this propagator perturbation theory is the best of two worlds, being able to do Lagrangian perturbation theory, but getting Eulerian quantities out of it without much difficulty. And there are two very nice applications. One of them has been recently done by Natalia Porqueras with the Lyman alpha forest. And Oliver will talk about how you can use this formalism to set accurate initial conditions for cosmological simulations based on two fluids. Thank you for listening. I'm looking forward to answering your questions. Bye.